The Hubble Space Telescope's resolution was limited, and in distant galaxies, individual Cepheids could blend with neighboring stars that would inflate their apparent brightness and skew the distances. This was a reasonable objection. JWST eliminated it. The telescope's infrared instruments and superior angular resolution could resolve individual Cepheids in galaxies where Hubble saw blurs. Rias's team re-observed the same Cepheid fields with JWST and compared the results. The mean discrepancy between Hubble and JWST Cepheid measurements was 0.03 magnitudes. To explain the tension between 73 and 67.4, you would need a systematic error of 0.18 magnitudes. The actual discrepancy was 6 times smaller than what the critics needed. JWST confirmed the local measurement, 72.6 plus or minus 2.0. The Hubble tension is real. It is not a calibration problem. It is not instrument noise. Two of the most precise measurements in the history of physics, measuring the same quantity, disagree at a statistical significance of 5 sigma, and then a massive instrument in the Arizona desert made it worse. Wendy Friedman has spent decades trying to resolve this argument. She leads the Carnegie-Chicago Hubble program, and her approach deliberately avoids the Cepheid method that Rias uses. Instead, her team measures distances using the tip of the red giant branch method. Red giant stars, when they reach a specific phase of helium ignition in their cores, all achieve nearly the same peak luminosity. This makes them a standard candle, just like Cepheids, but one that is less sensitive to dust and crowding, because red giants are intrinsically brighter in the infrared and easier to isolate in crowded fields. Friedman's result, somewhere between 69 and 72 kilometers per second per megaparsec, right between Rias and Planck. On the surface, this should help narrow things down. A third independent measurement, landing between the other two, might point toward the true value. It did the opposite. Friedman's number does not confirm Rias. If the tip of the red giant branch method is more reliable than Cepheids, then the local Hubble constant is lower than 73, and Rias has a systematic error his team has not found. But Friedman's number does not confirm Planck either. 69 to 72 is still higher than 67.4. The cosmic microwave background prediction remains too low. Instead of 2 camps, there are now 3. Each team has spent years refining their methods. Each team accuses the others of unresolved systematic errors. Rias says the Cepheid calibration is solid, and JWST proved it. Friedman says her method is cleaner and less assumption dependent. Planck's team says the cosmic microwave background measurement is the most fundamental because it relies on physics, not on local distance calibrations that can go wrong in 100 subtle ways. The disagreement is not just scientific. Careers have been built on these measurements. Grant funding flows toward teams that can claim the most precise value. Tenure decisions, conference invitations, and publication prestige all ride on whose number is right. Admitting a systematic error would mean admitting that years of work contained a flaw that the team failed to catch. Nobody volunteers for that. The institutional dynamics are real, and they slow down resolution. But behind the human politics, a deeper question remains. What if none of the measurements are wrong? What if 73 and 67.4 and 69 to 72 are all correct, each measuring the expansion rate at a different epoch or through a different physical pathway, and the reason they disagree is that the model connecting them is broken? The standard cosmological model, lambda-cold dark matter, predicts a specific relationship between the early universe's expansion rate and today's expansion rate. If that model is correct, the cosmic microwave background value and the local value must agree. They do not. If the model is wrong, they would not have to agree. And the disagreement would not be an error to fix. It would be evidence. Evidence that something about the bridge between the early universe and the late universe is missing from the equations. The Hubble tension sat in this unresolved state for years. Both sides dug in. JWST confirmed the local side. Planck remained solid on the early side. The gap persisted. And then, in March 2024, a different instrument produced data that suggested the bridge between early and late universe might indeed be broken, in a way nobody had anticipated. The Dark Energy Spectroscopic Instrument sits at the Mile Telescope on Kitt Peak in southern Arizona. It is not a space telescope. It is a ground-based machine designed for one purpose: to map the three-dimensional positions of tens of millions of galaxies and quasars across 11 billion years of cosmic history. Its instrument is built around 5,000 robotic fiber optic positioners, each one capable of independently targeting a different object in the telescope's field of view. In a single exposure, it can simultaneously collect the spectra of 5,000 galaxies. Over its planned 5-year survey, it will map roughly 40 million objects, constructing the most detailed map of the universe's expansion history ever assembled. The quantity it measures is the baryon acoustic oscillation signal. In the first few 100,000 years after the Big Bang, sound waves propagated through the hot plasma of the early universe. When the plasma cooled and the universe became transparent, those sound waves froze in place, leaving a characteristic spacing in the distribution of galaxies. That spacing acts as a cosmic ruler. Measure how it appears at different redshifts, and you can track how the universe has expanded over time. In March 2024, the instrument released its Year 1 results. The team had mapped roughly 6 million galaxies and quasars from the first year of observations. When they fitted the data to a cosmological model, something unexpected appeared. The equation of state parameter for dark energy, labeled W0, came out at negative 0.752 plus or minus 0.057. In the standard lambda cold dark matter model, this parameter should be exactly -1. -1 means dark energy is a cosmological constant. It does not change. It has the same strength everywhere, at all times, from the beginning of the universe to its end. Albert Einstein introduced it in 1917 and later called it his greatest blunder. In 1998, two teams independently discovered the universe's expansion is accelerating, and the cosmological constant was resurrected as the explanation. For 25 years, W equals -1 has been the default assumption. -0.752 is not -1. The Year 1 result was a 2.8 sigma signal. In physics, 2.8 sigma means there is roughly a 1 in 200 chance the deviation is random noise, suggestive but not conclusive. Most anomalies at this significance level disappear with more data, but by January 2026, the instrument had processed more of its survey data. The signal did not disappear, it strengthened. The latest analysis pushed the significance to 4.2 sigma. The threshold for a formal discovery in particle physics is 5 sigma, which corresponds to a 1 in 3.5 million chance of a random fluctuation. 4.2 sigma is not there yet, but it is close. Close enough that the cosmological community cannot ignore it. If dark energy is not a constant, if it is weakening over cosmic time, the consequences ripple through every model of the universe's past and future. The expansion history changes. The relationship between the early and late universe shifts. And perhaps most importantly, it might connect to the other crisis that JWST has been documenting since 2022. Because in November 2025, a paper appeared that drew a line between the expanding universe and the impossible galaxies. The paper, published in November 2025, proposed something that had been whispered about in cosmology seminars, but rarely stated in print. The anomalies JWST keeps finding in the early universe and the Hubble tension measured in the late universe might share a single cause. The logic works like this. If dark energy was stronger in the early universe than it is today, the expansion history between then and now would differ from what lambda cold dark matter predicts. The early universe would have expanded differently. The relationship between redshift and cosmic time would shift. An object observed at redshift 14 would not correspond to 290 million years after the Big Bang. It might correspond to a slightly different age, under slightly different conditions, with slightly different densities and temperatures. That difference, even if small, compounds across every calculation that depends on the expansion history. Galaxy masses, inferred from luminosity, depend on the assumed distance, which depends on the expansion history. Star formation rates depend on the time available. Black hole growth calculations depend on the time between the Big Bang and the observed epoch. Change the expansion history, and you change the denominator in every one of those calculations. The paper used the dark energy spectroscopic instrument's evolving dark energy parameters to construct an alternative expansion model labeled W0 WA cold dark matter. The authors recalculated predicted galaxy populations, star formation rates, and black hole growth timelines under these modified conditions. Several of the JWST anomalies that seemed impossible under lambda cold dark matter became less severe, not fully resolved. The galaxies were still more massive than expected. The black holes were still larger than standard accretion models allow, but the gap between observation and prediction narrowed. The impossible became merely improbable, and the Hubble tension, under this same modified expansion history, also eased. The predicted early universe value for the Hubble constant shifted slightly, reducing the gap between the Planck measurement and the local measurement. Two separate crises, one in the early universe observed by JWST, and one in the expansion rate measured by competing teams, partially dissolving under the same modification to the same model. When a single change to a theory simultaneously addresses multiple independent problems, it carries more weight than a patch that fixes only one. Patches are cheap, connections are expensive, but elegance is not proof. The modified model introduces new free parameters. More free parameters make any model more flexible, and more flexibility means it can fit more data regardless of whether it is physically correct. Critics pointed this out immediately. You can always improve the fit by adding knobs to turn. The question is whether the knobs correspond to real physics. The dark energy spectroscopic instrument is still collecting data. Its full 5-year survey will not be complete until roughly 2026. Each additional year either strengthens or weakens the 4.2 sigma signal. If it crosses 5 sigma with the full dataset, the case for evolving dark energy becomes difficult to dismiss. And if evolving dark energy truly connects the two biggest anomalies in modern cosmology, the standard model does not need patches. It needs replacement. But replacement with what? The consequences of weakening dark energy extend far beyond galaxy formation and expansion rates. They reach all the way to the end. For 25 years, the default picture of the universe's future has been defined by the cosmological constant. If dark energy maintains its current strength indefinitely, the expansion of the universe will continue to accelerate. Galaxies outside our local group will recede faster and faster. Their light will redshift beyond detection. One by one, they will cross the cosmic horizon and disappear from view. Given enough time, the observable universe will shrink to our local cluster of galaxies, then to our single merged galaxy, then to isolated stellar remnants cooling in an expanding void. This is the heat death scenario, not a dramatic explosion. A slow fade to maximum entropy, where every usable source of energy has been exhausted and the universe drifts toward absolute cold over timescales measured in trillions of years. Some versions of this scenario are more violent. If dark energy were to strengthen over time rather than remain constant, the acceleration would eventually tear apart galaxy clusters, then galaxies, then stellar systems, then atoms. This is the Big Rip, a hypothetical endpoint where the expansion rate becomes infinite in finite time. Both of these outcomes assume dark energy stays the same or gets stronger. The dark energy spectroscopic instrument's data suggests the opposite. Dark energy appears to be weakening. If W0 is truly negative, 0.752, and trending in the direction the data indicates, then the accelerating expansion will not continue indefinitely. At some point in the far future, dark energy's push will diminish below the threshold where it overpowers gravity. Gravity, which has been losing the tug-of-war against dark energy for the past 5 billion years, would begin to win again. The expansion would slow, then stop, then, potentially, reverse. The universe would begin to contract, slowly at first, then faster. Galaxies that had been racing apart would begin falling toward each other. The temperature of the background radiation would rise as space itself compressed. Structures that took billions of years to form would be crushed back together. The endpoint, carried to its logical extreme, would be something like the reverse of the Big Bang, a collapse to a singularity, the Big Crunch. This is speculative. The extrapolation from current data to cosmic endpoint spans timescales that dwarf the current age of the universe. Small uncertainties in today's measurements amplify into enormous uncertainties in predictions that extend 20 or 50 or 100 billion years into the future. No physicist would stake their reputation on a specific timeline, but the direction matters. For a quarter century, the assumption has been that the universe expands forever. The dark energy spectroscopic instrument's data does not confirm that assumption. Combined with JWST's evidence that the early universe was radically different from what models predicted, a new picture is forming. The universe might not be an eternal expansion. It might have a beginning, a middle, and an end. And the early universe that JWST is revealing, with its impossible galaxies and premature chemistry and oversized black holes, might be telling us something about the conditions at the beginning that we have never properly understood. Because JWST was not finished, the most distant galaxies and black holes were only part of the story. The telescope also found structures at scales larger than individual galaxies, appearing billions of years ahead of schedule. Return to the 6 galaxies from the Sears survey, the ones that launched the crisis in February 2023. After the overcounting scandal, after the recalibrations and spectroscopic confirmations, the revised masses came down. The original estimates of 10 to 100 billion solar masses were inflated. The corrected values were lower. Critics declared victory. Headlines moved on. The crisis was over, except the revised masses were still too high. In 2025, the Renaissance simulations, one of the most sophisticated cosmological simulation suites ever built, attempted to reproduce the JWST observations within the standard lambda cold dark matter framework. The team used a specific modification, a top-heavy initial mass function. In standard stellar physics, when a cloud of gas collapses and fragments into stars, the resulting population follows a predictable distribution. Lots of small stars, fewer medium stars, very few massive stars. This distribution, called the initial mass function, has been measured in the Milky Way and appears to be roughly universal. The Renaissance simulations proposed that in the early universe, conditions were different enough to shift this distribution. More massive stars per cloud, fewer small ones, a top-heavy function. The effect on inferred galaxy masses is significant. When you observe a distant galaxy, you measure total light output and convert it to stellar mass using assumptions about the mix of stars present. If the mix skews toward massive, luminous stars, you need fewer total stars to produce the same light. The inferred mass drops. The Renaissance team showed that a top-heavy initial mass function could reduce the inferred masses of JWST's anomalous galaxies by roughly a factor of 10, enough to bring some of them within the range lambda cold dark matter allows. This was presented as evidence that the standard model can survive, and it might. But the argument has a circular quality that critics were quick to identify. The initial mass function has been measured locally and appears universal. Invoking a non-universal mass function specifically to save the model is not independent evidence. It is a patch designed to produce the needed result. If the early universe's initial mass function was truly different, that itself demands an explanation. What physical conditions in the first few 100 million years produced a fundamentally different star formation process? The answer is unknown. The simulation works mathematically. Whether it corresponds to reality is a separate question entirely. Meanwhile, The corrected galaxy masses, even with the most favorable initial mass function assumptions, still sit at the upper edge of what lambda-cold dark matter permits. The overcounting scandal made the problem quieter. The Renaissance simulations made it more sophisticated. Neither made it go away. Each anomaly generates a proposed fix. Each fix partially works. And each partial fix leaves a residual that accumulates alongside every other residual from every other partial fix. One unexplained residual is a loose thread, 10 of them, all pointing in the same direction, all demanding that the early universe was more active and more structured than the standard model allows, is something else entirely. For 25 years, astronomers told a simple story about the first billion years. The universe began as a hot, smooth soup of hydrogen and helium. Gravity slowly pulled gas into clumps. Those clumps became the first tiny, metal-poor protogalaxies. Small things merged into bigger things over billions of years. Dust was a late arrival. Metals were a late arrival. Structure was a late arrival. Everything built up gradually, like sediment layering on an ocean floor. JWST found the ocean floor already covered. The sediment was already deep. In 2024, a class of objects called red monsters appeared in the data. They are massive, dusty galaxies sitting inside the first billion years after the Big Bang, and they violate every part of that simple story simultaneously. Each one is nearly the size of the Milky Way. Their dust content is high. Their star formation rates run at double modern levels. And dust is the critical detail, because dust is not simple. Dust is made of metals. Metals are forged inside stars. Stars must live, burn through their fuel, and explode before they scatter metals into the surrounding gas. That gas must cool, collapse, form new stars, and repeat the cycle. Each generation takes hundreds of millions of years. The dust inside a red monster represents the accumulated output of multiple stellar generations that somehow completed their entire life cycle within a window that should not have been long enough for even one. The protogalaxy story said the first billion years would produce small, fragile, metal-starved objects. Instead, JWST found fully operational galactic ecosystems. Dust and metals and structure and size, all present at once, all impossibly early. It is not that one measurement is off. Every measurement is off in the same direction. The early universe was not assembling slowly. It was already assembled. Red monsters sit alongside the impossible massive galaxies from the CRS survey, but they add a dimension those earlier discoveries lacked. The CERS galaxies were defined by their stellar mass. Red monsters are defined by their completeness. A galaxy can be massive without being chemically mature. A galaxy can have a lot of stars without having processed those stars through enough generations to produce significant dust. Red monsters have everything. They are not just big, they are finished. They look like galaxies that have been evolving for 5 or 6 billion years, except they exist at an age when the universe had barely celebrated its first billion. The standard patches do not work here. Top-heavy initial mass functions can reduce inferred stellar masses, and that helps with the CERS problem. But top-heavy initial mass functions do not produce more dust. They produce less. Massive stars burn hotter and faster, and their supernovae are more energetic, which actually destroys dust grains in the surrounding medium rather than creating them. The patch that partially fixes one anomaly makes this one worse. Bursty star formation models face a similar wall. If star formation happens in intense, brief episodes separated by quiet periods, you can build up stellar mass quickly, but building up dust requires continuity. You need sustained chemical enrichment across multiple generations, not a single violent burst. The burst makes stars. It does not make the dust that red monsters clearly contain. So the early universe was not just making stars faster than expected. It was running a complete chemical factory, cycling material through generation after generation of stellar evolution at a pace that no known mechanism can reproduce. And if single galaxies can achieve this, the next question becomes obvious. could groups of galaxies do it too? The answer arrived from a survey that was not even looking for it. JADE, the JWST Advanced Deep Extragalactic Survey, had been mapping the most distant galaxies in unprecedented detail. Among its targets was a region where galaxies appeared to cluster unusually close together at high redshift. Follow-up observations revealed something that forced the problem to jump up an entire scale. JADE's ID1 is a protocluster, not a single galaxy. A gravitationally bound group of 66 or more galaxies, all sitting at roughly 1 billion years after the Big Bang. X-ray observations registered gas between the member galaxies at temperatures exceeding 1 million degrees. Hot, intracluster medium. The kind of superheated gas that forms when galaxies have been gravitationally interacting for extended periods, their halos colliding and shock heating the intergalactic material. The previous record for a structure like this was 3 billion years after the Big Bang. JADE's ID1 arrived 2 billion years ahead of schedule. Galaxy clusters are the largest gravitationally bound structures in the universe. The Virgo cluster contains over 1,000 galaxies. The Coma cluster spans roughly 20 million light-years. These structures take enormous amounts of time to assemble because they require galaxies to form first, then fall toward each other under gravity, then virialize into a stable configuration. Each step operates on timescales measured in billions of years, not hundreds of millions. Finding a protocluster with hot intracluster gas at 1 billion years means every step in that sequence happened faster than any simulation can reproduce. This is where the pattern becomes impossible to ignore. Individual galaxies, too massive. Black holes, too heavy. Chemistry, too mature. Star formation, too efficient. 341 unidentifiable objects that vanished. And now, large-scale structure forming billions of years too early. Each anomaly, taken alone, could be treated as an outlier, a statistical fluctuation, a measurement error that would eventually be corrected. Taken together, they point in one direction. The model that predicts when each of these things should appear is consistently wrong, and it is wrong in the same way every time. Everything is too early. Everything is too complete. Everything looks older than the universe allows. The standard model of cosmology, lambda CDM, was built to explain the large-scale structure of the universe. Its predictions for the cosmic microwave background are extraordinary. Its description of the cosmic web at low redshift matches observations beautifully. It is one of the most successful models in the history of physics. And it cannot produce what JWST sees in the first billion years. Not the galaxies, not the black holes, not the chemistry, not the clusters. Some of these anomalies might yield to clever modifications. The Renaissance simulations showed that top-heavy initial mass functions can reduce inferred galaxy masses by roughly a factor of 10. That helps with one problem. It does not help with dust or clusters or black hole masses or the 341 little red dots or the chemical enrichment timeline or the star formation efficiency measurements. Each patch fixes one leak and ignores the others. But before the question of whether lambda CDM can survive, there is a more immediate puzzle. The universe transitioned from an opaque fog to transparent space during its first billion years, in a process called reionization. Astronomers thought they understood how it worked. JWST proved they did not. Reionization is one of the great phase transitions in cosmic history. For the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen. Opaque, light could not travel freely. Then, the first luminous objects began producing ultraviolet photons, ionizing the surrounding hydrogen, clearing bubbles of transparency that gradually merged until the entire universe became see-through. The textbook timeline placed the end of this process somewhere around redshift 6, roughly 1 billion years after the Big Bang. The mechanism was straightforward. Early galaxies and quasars produced the photons. The fog cleared gradually. Simple. JWST found it ended earlier than the models predicted, closer to redshift 9. That is not a small shift. Redshift 9 corresponds to roughly 550 million years after the Big Bang. Moving the endpoint by 450 million years means the universe became transparent far sooner, which means there were far more ionizing photons far earlier than any known source can account for. This is the photon budget crisis. Add up every galaxy JWST has found in the early universe. Add every quasar. Add every active galactic nucleus. Add the little red dots if you assume they are all active galactic nuclei, producing ionizing radiation at maximum theoretical output. The total number of ionizing photons still falls short of what was needed to clear the fog by Redshift 9. Something was producing ultraviolet radiation in the early universe that has not been identified. An unknown source of photons, powerful enough to ionize hydrogen across cosmological volumes, that is either invisible to current instruments or belongs to a category of objects that has not been theorized. Dark stars could fill the gap. If Catherine Fries's model is correct, supermassive dark stars, powered by dark matter annihilation, would have been extraordinarily luminous in ultraviolet wavelengths. A single dark star of 1 million solar masses could produce as many ionizing photons as an entire dwarf galaxy. If dark stars were common in the first few 100 million years, they would be precisely the missing source the photon budget needs. They would also be invisible after their dark matter fuel ran out, explaining why no local counterpart exists. The photon budget crisis connects to nearly every other anomaly JWST has uncovered. If there were more luminous sources in the early universe than current models account for, those same sources would contribute to the unexplained brightness that makes early galaxies appear too massive. Some fraction of the impossible stellar mass might not be stellar mass at all. It might be the light from objects that are not galaxies, counted as galaxies because nobody knew to look for anything else. This is the thread that ties the investigation together. The impossible galaxies, the overmassive black holes, the mature chemistry, the early clusters, the little red dots, the photon budget crisis. They are not separate problems. They are symptoms of the same underlying condition. The census of the early universe is wrong. The catalogue of objects that could exist in the early universe was incomplete. JWST is finding things that were never in the inventory, and the total energy output of the early universe exceeds what every object in that inventory can produce, which means the inventory itself is the problem. The evidence no longer points at individual broken predictions. It points at a model that is missing something fundamental. The question is what? Step back from the individual anomalies and map the full scope of what JWST, DESI, and Chandra have collectively revealed in 3 years of observation. 1. Galaxies 10 to 100 times more massive than any model predicted, sitting at redshifts above 10 within the first 500 million years, confirmed across multiple surveys, revised downward after recalibration, still too massive. 2. A supermassive black hole at 470 million years that weighs as much as every star in its host galaxy. Ratio 100 to 1,000 times higher than any black hole in the local universe. Detected through gravitational lensing and 2 weeks of Chandra X-ray observation. 3. Oxygen at 290 million years. Nitrogen at 430 million years, with a ratio 4 times higher than anything in our own stellar neighborhood, and polycyclic aromatic hydrocarbons at 900 million years. 3 independent chemical signatures, each requiring timescales the universe had not yet provided. 4. Star formation efficiency above 50% in blue monsters, against a universal average of 10%. Some early estimates from CERs approached 100%. No known feedback mechanism allows this. 5. 341 little red dots between redshifts 5 and 10, matching no known astronomical object, with active galactic nucleus densities 50 times higher than predicted. One of them, the cliff, produces a Balmer break that fits no existing template. The entire population vanished without leaving descendants. 6. A tentative helium-2 absorption line at 1640 angstroms in JWST GSZ 140, consistent with a supermassive dark star powered by dark matter annihilation. Signal-to-noise ratio roughly 2. Not proof, a whisper. 7. The Hubble tension confirmed as real by JWST, with local measurements at 73 km per second per megaparsec, and cosmic microwave background measurements at 67.4, a gap of 8% at 5 sigma significance that is not caused by instrument error. 8. Dark energy showing signs of weakening over cosmic time, with DESI measuring the equation of state parameter at negative 0.752 instead of negative 1, now at 4.2 sigma significance and approaching the 5 sigma discovery threshold. 9. A protocluster of 66 or more galaxies with million-degree intracluster gas at 1 billion years, 2 billion years before any simulation predicted such a structure could exist. 10. More ionizing photons in the early universe than every known source combined can produce. An unidentified contributor to reionization that cleared the cosmic fog earlier than any model accounts for. 10 independent anomalies, discovered by different teams using different instruments across different redshifts. Each one challenges a specific prediction of the lambda CDM model. Together, they describe a universe that was far more complex, far more energetic, and far more structured in its first billion years than the reigning model of cosmology allows. Any one of these could be a fluke. Any two might be coincidence. But 10 anomalies, all pointing in the same direction, all saying the early universe was more advanced than predicted, is a pattern. And the question the pattern raises is not about galaxies or black holes or chemistry. It is about whether the model that has governed cosmology for 25 years can survive what JWST has found. The model has defenders, and their arguments are not trivial. Lambda CDM has been the standard model of cosmology since the late 1990s. It describes a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, expanding from a hot initial state, according to general relativity. Its predictions for the cosmic microwave background match observations to extraordinary precision. Its description of large-scale structure at low redshift, the cosmic web of filaments and voids, is confirmed by galaxy surveys spanning millions of objects. It predicted the accelerating expansion of the universe before supernovae confirmed it. By almost any measure, Lambda CDM is one of the most successful physical models ever constructed. An entire generation of cosmologists built their careers on it. Grants were written against its predictions. Tenure cases were argued on its framework. Textbooks were organized around its timeline. The intellectual and institutional investment in Lambda CDM is immense, and that investment is not purely scientific. It is personal and professional. Declaring a crisis in the foundational model of your field is not a neutral scientific act. It has consequences for funding, for reputation, for the validity of decades of published work. The resistance to abandoning Lambda CDM is not irrational. It is human, and the resistance has produced real results. The Renaissance simulations, published in 2025, demonstrated that incorporating top-heavy initial mass functions into Lambda CDM can reduce the inferred stellar masses of early galaxies by roughly a factor of 10. A top-heavy initial mass function means the first generation of stars were predominantly massive rather than following the distribution observed in the local universe. If early stars were heavier on average, fewer of them would produce the same amount of light. The galaxies would appear less massive than photometry initially suggested. This matters. It means some of the most headline-grabbing claims from 2023 were genuinely overcounted. The media reported impossible galaxies because the mass estimates were inflated by calibration errors and assumption errors. The corrections brought some objects back within Lambda CDM's tolerance. The overcounting scandal was real, and it damaged the credibility of the crisis narrative. But it did not make the crisis disappear. The The corrected masses are still too high. Reduced by a factor of 10, yes. But lambda CDM's predictions were exceeded by factors of 10 to 100. Cut in half, the anomaly remains. The correction made the problem less dramatic. It did not make the problem go away. It made it quieter, and quieter problems in science are dangerous because they stop receiving attention while continuing to exist. The patches also introduce new tensions. Top-heavy initial mass functions help with stellar masses but worsen the dust problem. Bursty star formation models help with star formation rates but cannot explain chemical enrichment timelines. Early dark energy models help with the Hubble tension but have not been shown to resolve the galaxy formation crisis. Each patch addresses one symptom and is silent on the others. No single modification to lambda CDM has been proposed that simultaneously resolves all 10 anomalies. Not one, and there remains a class of objects that resists every proposed patch entirely. Objects that cannot be explained by recalibration, or different mass functions, or modified star formation histories. Objects that appear to require something genuinely new, 341 of them, return to the little red dots one more time, because their story has changed since the last time they appeared in this investigation. When they first surfaced in 2022, astronomers catalogued them as compact, high redshift galaxies. Small, red, unremarkable, except for their numbers. By 2024, spectroscopic follow-up revealed they were anything but unremarkable. Their active galactic nucleus densities were 50 times higher than any prediction. Their spectra did not match galaxies or quasars or any known template. The cliff produced a Balmer break that sits in empty theoretical space, and the population is bounded. They appear around redshift 10 and cluster densely between redshifts 5 and 8. Below redshift 5, they vanish, not gradually, completely. No astronomical population behaves like this. Galaxies evolve, they merge, they grow, they change color and morphology, but they leave descendants. Elliptical galaxies descend from merged spirals. Spiral galaxies descend from turbulent disk systems. Every type of galaxy observed in the local universe can be traced backward to a precursor population. The little red dots cannot be traced forward to anything. Whatever they are, they stopped being it, and nothing recognizable replaced them. Joel Lager's black hole star hypothesis offers the cleanest explanation available. If little red dots are direct collapse black holes wrapped in heated gas cocoons, their disappearance is natural. The cocoon is temporary. Dark matter and primordial gas funnel onto the collapsing object, heating the surrounding envelope to temperatures that produce emission, mimicking a stellar population. From the outside, through JWST's instruments, it looks like a compact galaxy, but it is one object. One enormous black hole accumulating mass inside a glowing shell. The cocoon phase lasts as long as the fuel supply holds. When the surrounding gas is consumed or dispersed by the black hole's own radiation, the cocoon fades. What remains is a naked, supermassive black hole, invisible at optical and near-infrared wavelengths. The little red dot did not evolve into something else. It shed its skin. The chrysalis dissolved, leaving only the black hole at the center, which then became the seed around which a proper galaxy eventually formed. If this is correct, the relationship between black holes and galaxies is inverted. The standard picture says galaxies form first, and black holes grow later inside them. Lehar's model says black holes form first, wrapped in a brief, visible cocoon, and galaxies crystallize around the black hole afterward. The little red dots were not a type of galaxy. They were the embryonic phase of supermassive black holes, visible for a cosmic instant, then gone. This would explain UHZ1. A black hole weighing as much as every star in its galaxy would make sense if the black hole came first and the galaxy was still catching up. It would explain the impossible mass ratios. It would explain the mature chemistry, because the cocoon phase would involve intense radiation processing gas at extreme temperatures. And it would explain the vanishing act. Between redshift 5 and the present day, billions of years passed. Plenty of time for galaxies to grow around the seeds, burying the evidence of the cocoon phase beneath layers of ordinary stellar evolution. 341 cocoons, 341 seeds, and if each one became the core of a galaxy, then the supermassive black holes at the centers of galaxies across the observable universe may all trace their origin to a brief, violent phase that nobody knew to look for until JWST pointed its mirror at the deep past. Beyond the Big Bang, the phrase has appeared in headlines since JWST's first anomalies surfaced. It sounds like it means before the Big Bang. It does not. Or at least, it did not used to. What beyond the Big Bang originally meant in the context of JWST was straightforward. The telescope is finding things that the standard Big Bang model cannot produce. Run the clock forward from the initial singularity, through nucleosynthesis, through recombination, through the Dark Ages, through the formation of the first stars, and you cannot arrive at what JWST observes at 290 million years. The physics does not connect point A to point B. The model that starts with the Big Bang and runs forward falls short. In that sense, the observations are beyond what the Big Bang framework can explain, but the data has pushed the conversation somewhere more uncomfortable. JWST already contains oxygen at 290 million years. Oxygen requires at least one full stellar generation to form. A massive star must ignite, burn through hydrogen and helium on its main sequence, fuse carbon and oxygen in its core, and explode as a supernova to scatter those elements into the surrounding gas. The fastest massive stars complete this life cycle in roughly 2 to 3 million years, but they need to form first, and before they form, gas must cool and collapse, which requires additional time. The most aggressive models place the first stars at roughly 100 million years after the Big Bang. That leaves 190 million years for a star to form, live, die, enrich its surroundings, and for a new generation to incorporate that enriched material into a detectable galaxy. It is possible, barely. But the nitrogen in GNZ, 11 at 430 million years, is harder. A nitrogen to oxygen ratio 4 times solar requires not one but multiple stellar generations, or supermassive stars of 1,000 to 100,000 solar masses that themselves need extreme conditions to form. And the polycyclic aromatic hydrocarbons at 900 million years require sustained chemical processing across generations of asymptotic giant branch stars. Each observation pushes the required starting conditions further back. If the chemical maturity JWST observes demands processes that need hundreds of millions of years to complete, and those processes must have already finished within the first few 100 million years, then the processes may have started before the epoch we can observe, before recombination, possibly before the Big Bang itself. This used to be philosophy. Roger Penrose proposed conformal cyclic cosmology, in which our Big Bang is merely the latest in an infinite series of cosmic cycles, each one beginning where the previous one ended. Cyclic models from Paul Steinhardt and Neil Turok describe colliding higher dimensional branes that periodically produce Big Bang events. Bouncing cosmologies propose that the universe contracted before expanding. Structure from a previous phase carried over into the current one. These frameworks were treated as mathematical curiosities, elegant but untestable. JWST has not proven any of them correct, but it has produced observations that seem to demand conditions prior to the standard starting point. The first few 100 million years were not simple. They were not a blank slate of hydrogen and helium slowly assembling. They were complex from the start, and complexity, at the start, implies conditions that produced it, which implies something came before. The conversation has moved from beyond what our model predicts to beyond what our model's starting point allows. That is a different kind of beyond entirely. Return to the helium-2 absorption line at 1640 angstroms. Because if it is real, it does not just confirm dark stars, it cascades. Dark matter makes up 27% of the total mass energy content of the universe. It shapes the rotation curves of galaxies, governs the formation of large-scale structure, bends light through gravitational lensing, and leaves its imprint on the cosmic microwave background. Its gravitational effects are measured with extraordinary precision, but dark matter itself has never been directly detected. No particle collider has produced it. No underground detector has registered it. No telescope has observed its interaction with ordinary matter through any force other than gravity. Catherine Freese's dark star model changes that. If dark matter particles annihilate inside primordial gas clouds, the energy released would heat the gas and prevent it from collapsing into a normal star. Instead, the cloud would swell into a supermassive dark star, potentially reaching 1 million solar masses, powered by the annihilation of dark matter particles in its core. The helium-2 absorption line at 1640 angstroms is a predicted signature of this process. Ionizing helium twice requires extreme temperatures that dark matter annihilation naturally produces, but that early stellar populations cannot easily reach. The signal in JWST 140 is tentative. The signal-to-noise ratio hovers around 2. In physics, that is not a detection, it is a hint, a whisper in the noise that could be real or could be an artifact of the data reduction pipeline. Confirmation requires deeper spectroscopic observation, ideally of multiple candidates, with signal-to-noise ratios above 5. But consider what confirmation would mean. The most distant spectroscopically confirmed object in the universe would not be a galaxy, it would be a single star. The census of the early universe would require fundamental revision. Every bright, compact source at extreme redshift would need to be re-examined as a potential dark star candidate. Some fraction of the impossible galaxy masses might dissolve, because those bright dots are not collections of billions of stars. They are individual objects, producing galaxy-scale luminosity through a mechanism that was not in any model before 2023. Dark stars could also resolve the photon budget crisis. A supermassive dark star would be an extraordinarily powerful source of ionizing ultraviolet radiation. If dark stars were common in the first few 100 million years, they would contribute exactly the missing photons that the reionization budget requires. The unknown source that cleared the cosmic fog earlier than expected might be dark stars, burning through their dark matter fuel and flooding the universe with ultraviolet light before collapsing into the seeds of supermassive black holes. One confirmation could solve 3 problems simultaneously: the impossible galaxy masses, the photon budget deficit, and the mystery of what preceded supermassive black holes. Dark stars form, shine briefly, exhaust their dark matter fuel, and collapse. The remnant is a massive black hole seed. Wrap that seed in accreting gas, and you have something that looks remarkably like a little red dot. The sequence has not been formally established, but it is suggestive. Dark stars collapse into heavy seed black holes. Heavy seed black holes accrete gas cocoons. Those cocoons eventually shed, and what remains becomes the supermassive black hole at the center of a galaxy, a whisper at 1640 angstroms. It could be noise. It could be the first direct evidence that dark matter does something other than pull. The difference between those 2 possibilities is about 3 years of telescope time. Catalog what JWST has revealed that nobody knew 3 years ago. We do not know how the first galaxies formed so quickly. Every proposed mechanism, from bursty star formation to top-heavy initial mass functions to modified feedback models, explains part of the observations and fails to account for the rest. The corrected galaxy masses are still too high. The star formation efficiencies are still physically impossible under known physics. The chemical enrichment timelines still require more stellar generations than the available time permits. We do not know how supermassive black holes reach tens of millions of solar masses within 500 million years. The heavy seed model provides a plausible pathway, but it has not been observationally confirmed. No direct collapse black hole has been caught in the act of forming. The model requires pristine, metal-free gas in sufficient quantities, and JWST's own chemical detections suggest metals appeared far earlier than expected, which narrows the window for pristine gas to exist. We do not know what the 341 little red dots are. The black hole star hypothesis is the best available explanation, but it remains a hypothesis. Spectroscopic confirmation of additional objects with anomalous Balmer breaks, combined with X-ray follow-up to detect embedded black holes, could take years. The cliff at redshift 3.55 still matches no template. An entire population of objects appeared and vanished from the cosmos, and the best explanation involves a category of astrophysical object that did not exist in any textbook before 2024. We do not know if dark stars exist. One tentative spectral line in one object at a signal-to-noise ratio of roughly 2 is not evidence. It is a direction to look. Confirmation or refutation depends on deeper observations that JWST can perform, but has not yet scheduled with sufficient depth. We do not know why the Hubble constant has two values. JWST confirmed the tension is real and not an instrument artifact. The local measurement and the cosmic microwave background measurement are both precise and both correct within their own frameworks. They disagree by 8% at 5 sigma. Either one measurement contains an unidentified systematic error that has survived 15 years of scrutiny by competing teams, or the model connecting the early universe to the late universe is missing a component. We do not know if dark energy is constant. DESI's measurement at 4.2 sigma is approaching but has not reached the 5 sigma threshold that physics requires for a discovery claim. If dark energy is weakening, the fate of the universe is not what textbooks describe. The expansion might not accelerate forever. It might slow and reverse. But this remains an extrapolation from incomplete data. We do not know what produced the excess ionizing photons that cleared the cosmic fog. We do not know how a protocluster of 66 galaxies with million-degree gas assembled 2 billion years before simulations say it could. We do not know whether the complexity JWST observes at 290 million years implies conditions that existed before the Big Bang. We do not know if the standard model needs patches or replacement. Before JWST, cosmologists thought they had answers to most of these questions. The answers were clean and internally consistent. The telescope did not provide better answers. It revealed that the questions themselves had been wrong all along. JWST has an expected operational lifespan of 20 years or more. Its fuel reserves, originally projected for 10 years, have been extended by the precision of its launch trajectory. The telescope arrived at L2 with enough station-keeping propellant to operate well into the 2040s. It is not winding down, it is beginning. DESI is still collecting data. Its Year 1 results produced 2.8 sigma evidence for evolving dark energy. By January 2026, that had strengthened to 4.2 sigma. Years 2 and 3 of data remain to be fully analyzed. If the signal holds or strengthens through the complete dataset, the cosmological constant that has anchored lambda CDM since 1998 will require replacement. On the ground, a new generation of telescopes is approaching first light. The extremely large telescope in Chile's Atacama Desert will carry a primary mirror 39 meters across, 5 times the diameter of any existing optical telescope. Its spectroscopic capabilities will resolve individual stars in distant galaxies that JWST can only image as smudges. The 30-meter telescope and the giant Magellan telescope will add complementary capabilities from different sites and different instrument configurations. Together, these 3 observatories will be able to do what JWST cannot. They will take spectra of the little red dots at resolution high enough to distinguish a compact galaxy from a black hole cocoon from a dark star. They will measure the helium-2 line at 1640 angstroms with signal-to-noise ratios sufficient to confirm or rule out dark matter annihilation as a power source. They will resolve the stellar populations inside red monsters well enough to count the chemical generations and determine whether the enrichment timeline is genuinely impossible or merely implausible. The central question this investigation started with has not been answered. It has gotten worse. Why does the early universe look nothing like our models predicted? 3 years of JWST data have not converged on a solution. They have diverged into deeper uncertainty. Each new observation raises a new variable. Each proposed explanation introduces a new tension. The map of what we know has barely changed. The map of what we do not know has expanded in every direction. Lambda CDM may survive. It has survived challenges before. Dark matter was added when rotation curves did not match. Dark energy was added when the expansion accelerated. The model has absorbed anomalies that would have killed a less flexible framework. It could absorb these too: top-heavy mass functions, modified feedback, early dark energy, heavy seed black holes. Each patch covers a portion of the problem. Perhaps enough patches will hold, or perhaps the patches are the problem. Perhaps a model that requires a new modification for every new observation is no longer a model. Perhaps what JWST has found is the outline of something else entirely, a different history.